going to speak about diagnostic aspects of Raman spectroscopy in the physics of semiconductor quantum-sized nanostructures.
First of all, I also would like to say my thanks to the organizers of this conference in so fine, beautiful city, and their kind invitation to make a report on this conference. Here is the title of my report and the names of my co-authors. You see that the title is wide enough due to the fact that at first we planned to make a small review, but due to the press timetable, I shall give you not wide review, but small report based on examples, several examples of in what way we can use Raman scattering for diagnostic of quantum-sized system. And I shall speak about such four examples. Well, we shall start with two-dimensional system. It is well known that Raman scattering for a long time is very popular method to study phonon frequencies. But from one phonon Raman scattering, we can obtain frequencies of optical phonons in the central point of brilliant zone. As to the acoustical phonons, study of acoustical phonons, as a rule, more often are used more complex neutron scattering. But the situation cardinally change when we look for two-dimensional system. For example, semiconducting superlattices. In this case, we have to use the idea about the folding of classical brilliant zone to the small brilliant zone, folded brilliant zone, depending on the new period of several nanometers or 10 nanometers typically. Therefore, in such way, you see that in the region of acoustical branches, TA, LA, due to the folding, we have a new optical type vibration in the center point of new small brilliant zone. This vibration of TA or LA type, in reality, in this picture are of optical type. Therefore, they can interact with light, and therefore, in Raman scattering in the low frequency region, typical for acoustical vibration, we can measure a new narrow enough lines, depending on the period of your superlattices. What is important, that the accuracy of obtaining frequencies of all the dispersion of all acoustical branch is much more better than for usual neutron scattering. The second example which I would like to discuss deals with graphite and graphene. Usually it is well known that for graphite we have one main G band. This is large intensity, and much smaller defect band there. Here we not see it due to the high quality of this specimen. But in many cases, here is, you may obtain D band comparable with G band. But situation in graphene, which was theoretically discussed in some publications of Professor Dresselhaus, from her publication, it is known that beside large G band in graphene, we also have more intense 2D band. You see the frequency double from D vibration in this region. This band also sometimes may be seen in ordinary graphite, but its intensity is 3, 4, 5 times weaker than main G band. The quality of electron bands and typical situation of electron bands in graphene is such that due to the resonant Raman scattering, the intensity of 2D bands rise, and you see, for example, in this example, that intensity is this maybe 2, 3, even 5 times larger than ordinary G band. What is important, that intensity of this 2D band depends on the number of layers of graphene. It is maximal in one layer system. In such case, it may be 4 or 5 times larger, and then it changes to lower intensity for 2 layers, 3 layers, and it's graphene. I can show you our results obtained in our experiments. With carbon-based composite derived from silicon carbide. You see that after long time sublimation at very high temperature, more than 2000 degrees of Celsius, we can obtain a different region from our specimen. Here is typical nano or micro carbon, but in large part of this specimen we see graphene areas of different thickness. Here is the Raman scattering. You see first spectra, green, is spectra for this region 1 of carbon, and all 3 another spectra, 2, 3, 4, are spectra obtained from graphene flakes. And the most intense spectra, red spectra, is obtained from graphene with really 1-layer graphene. Here is 2-layer graphene. You see comparable intensity. Therefore, Raman scattering spectra, as was discussed before in previous reports of our chief of our session, we see that Raman scattering is a very simple way to obtain knowledge about the not only graphene, fact of presence of graphene, but the quality of this graphene and number of graphene layer. Well, next, for the end of two-dimensional system, we discuss our results obtained with our French colleagues from Paris University. They were able to grow cadmium selenide nanoplatelets. this is specimens. You see the thickness of this specimen was 1, 2 molecular layer only, but this size is large enough, 40, 50 nanometers. They were able to grow 2 types of such nanoplates, pure cadmium selenide and cadmium selenide nanoplates covered by cadmium sulfide shell. But these specimens were of 2 types. First type, when we usually, as usual, well-known core shell quantum dots, shell cadmium selenide was for all side of your cadmium selenide, it is cadmium selenide, and in another case, shell was only on this 4 thick grain of this, not 6 side, but here, only here. This is the difference of this specimen. We measure absorption spectra. You can see that for such type of sample, we see such good exciton spectra, as was in previous report was shown. And the thickness, the size of this shell does not affect the position of this band. It is constant. But if we have shell in all sides, then larger thickness of shell, the position of, you see, pure cadmium selenide is the same cadmium selenide. With shell only 1 monolayer and shell 3 monolayer. You see the difference in position, and this change was discussed in our previous publication, and we showed that time that the effect is tunneling of excitonic excitation from cadmium selenide to wider size, to cadmium sulfide. And in this reason, we can see what is important, that next picture is our phonon Raman scattering for crown, shell, and next for all side core shell. And really, all our results obtained on phonon spectra coincided with previous result of absorption spectra. Well, and for the last part of my report, I would like to discuss the rule of Raman scattering in study of molecular beam epitaxial quantum dots. It is well known that mechanism of obtaining quantum dots by molecular beam epitaxy is Transky-Krastanov mechanism due to the very large strain between, for example, silicon and germanium epitaxial layer. It is caused by the difference, which is 4% between silicon and germanium. For example, for 3,5 compounds, indium arsenide, gallium arsenide, it is even 7%. Therefore, the strain is very large. And in this reason, when we have only 4 molecular layer of germanium on silicon, we have abrupt transition from layer to 3-dimensional growth. And in this way, we obtain different types of quantum dots. The form, shape of these quantum dots depend on thickness of germanium epitaxial layer, and temperature. You can see if compare this picture and this picture. They obtained is larger thickness, but more important, larger temperature. The theoretical background of this change from pyramids to domes was discussed theoretically by a group of IBM, Professor Teosov, and is shown in this slide. Really, he analyzed energy per one atom of these two forms, pyramids and domes, and shows that for small island, really preferable is pyramids, but after concrete volume, we have changed from pyramids to dome. Our experiments at first time really coincide with such situation. But then we compare the form of quantum dots with the change of temperature. And we obtain the next unusual for Stransky-Krasnov mechanism results that we have for larger temperature, the same thickness, we have back process, transition from domes to pyramids. The answer on this question, why we have non-usual for Stransky-Krasnov mechanism picture, was obtained from our Raman Scattering measurements. Really, if we have pure germanium quantum dots on silicon substrate, then we must see in Raman Scattering phonon bands from silicon, near 500 centimeters here, and from germanium. But in reality, picture is three mode, you see, between germanium vibration and silicon vibration. We obtained third band, typical for mixed silicon-germanium compound. Such measurements was studied many years ago by Cordono with co-workers, and really three-mode spectra are typical for mixed silicon-germanium. From frequencies of this point and their intensity may be obtained composition of this mixed silicon-germanium. It is presented on this table. You see that content of germanium is not pure in these quantum dots, but because silicon content is half to half, therefore the interdiffusion process due to the surface diffusion and effect of very non-uniform strain resulted to such so unusually giant interdiffusion that in reality we have near 50-50 silicon germanium. It is understandable that this is very important for application. For example, if you want to use cadmium selenide quantum dots for lasers and use cadmium selenide covered by shell cadmium sulfide, you must take into account this large in the diffusion, and as a result you obtain another line of your laser more wider in another position. Thanks you for attention.
Thank you, Professor, for this very wide and deep presentation. So now we have time for a couple of questions. Actually, in the peaks that you showed in the third case, if it's possible to go back with to the slide,
This.
Back. One more. Yeah, here.
Yeah.
I was puzzled by the relative intensity of the two cases in the bottom panel, cadmium selenide 5 over cadmium sulfide 3 versus cadmium sulfide 1. I mean, the two peaks, in addition to shift, they also change the relative intensity.
Yeah.
Do you have an explanation for that?
The peaks are, this picture are not normalized.
Okay.
Therefore, really, for wider, thicker shell, we have something larger intensity, but
no, I mean the relative two peaks.
Yeah.
You see, first and second peak.
Yeah.
Second peak is bigger than first peak in the red,
Yeah.
in the red curve. Instead, they get closer in intensity, maybe.
yeah, but
In blue case.
in all cases, it is important that cadmium selenide is the same, and the signal is from quantum confinement in cadmium selenide. But due to the shell, we have tunneling of excitation.
Yes, so you have exciton.
Therefore, signal in all
Shift.
three cores are from cadmium selenide.
This is clear.
Signals from cadmium selenide is the same.
So if there are no more questions, we thank our speaker again.